There we go. So I'm starting the YouTube stream right now. Yeah, I got it all set up, and then just forgot to click the button.
Yeah, that's fine. I'm just on my phone, so it's comfortable to watch through YouTube for me.
Oh, okay,
So,
gotcha.
all right. Thank you.
Mm-hmm. All right. Are you driving?
Me?
Yeah.
No, I'm just in the kitchen. I'm not on the PC.
Okay, okay, okay. I just want to make sure that because I know one of you, is driving on your way home. Um, and I know that it's difficult because this class is not entirely audio. There's definitely a visual aspect to it, and I don't want people to do something that is unsafe. That's all.
All right. Thank you very much.
No problem. All right, so now we want to define the overflow flag for subtraction because there's a different way to define overflow for addition, but right now we are focusing only on subtraction. So I'm going to use O little v, because otherwise it looks like a zero or looks like false, so I don't want people to accidentally mistake, O uppercase O as a zero. So overflow is defined to be x n minus 1, which is the most significant bit of the minuend, and the negation of y n minus 1, which is the most significant bit of the subtrahend, and this is the negation of d n minus 1, which is the most significant bit of the difference. So this is one way to get an overflow. And then the other scenario of an overflow is the negation of x n minus 1, y n minus 1, d n minus 1. So if you think about it, if you want the overall OR to be a 1, then you need one of the two conjunctions to be true. If you want this conjunction to be true, then you need x n minus 1 to be a 1, y n minus 1 to be a 0 so that the negation is a 1, d n minus 1 to be a 0 so that the negation is a 1, then that will make this entire thing a 1. Now the other side is kind of the flip side of the coin, so I'm not going to explain that. But this is the definition of overflow. This is how it is calculated. So now we got a few things, right? So right now, we also have the sign flag. The sign flag, has its own name, even though it really is just dn minus 1. It really is just the most significant bit of the difference. Okay? So between these two, okay, we can know the result of a comparison, a signed comparison for sure. So we're gonna go through, well, let me see, 1, 2, 3, 4. I'm just thinking about how many scenarios I want to go through, just so that we can see the pattern. Okay. Um. Well, the patterns we have seen already, so I'm gonna flip back to the earlier notes, just so that we can go back and reuse those examples. So we're gonna reuse this one here. So with this one, what is OV, right? What is the overflow flag? The overflow flag is going to be a 1 in this case, because x n minus 1 is a 1, y n minus 1 is a 0, and d n minus 1 is also a 0. So overflow is going to be a 1 in this case. Let's take a look at this one here. Okay, I just want to make sure that my hovering over the tablet is detected. There we go. So in this case, x n minus 1 is a 0, y n minus 1 is a 1, and then d n minus 1 is a 1. So this one also has an overflow of 1. So let me check the text channel and see if there are any questions about how overflow is computed. I don't see any questions. So are we doing okay? Are these examples illustrating how overflow is computed? And in both of these cases, overflow is a 1.
Can you show us the equation one more time,
Absolutely. So the
please?
equation is right here.
can we do just an example where we see that equation in effect?
Okay, I can do this. Okay, so what I can do is I can copy the equation to the other slide. So we'll do a copy here, and then we swing back here, paste it here, and let me see, can I, yep, I can drag it around a little bit like so. Okay, there we go. Alright, so now, is that okay? This is the equation. These are the values. These are the values. So the question is, how are we, so the question is, how are we computing the value? The value of the overflow flag. Is that making any sense?
Right. I was just thinking maybe there was we can take one of these x and y values and then plug them into this equation.
Oh yeah, I'm asking you to do it.
Oh, well, I need a second then.
Yeah, so I'm having you guys to do it so that you have you actually do some hands-on here. So let me go back to the pen tool. Because in this case, n is 4. We are dealing with 4-bit integers. So you just substitute n being 4, in when we do the calculation of overflow. And we have x, y, and also d defined in this case. And then we also have x, y. We also have x, y, d defined in this case. So the idea is we just focus on the most significant column and the most significant column here. This is x n minus 1, this is y n minus 1, this is d n minus 1, and same way over here. And you just have to kind of convince yourself that when you substitute the values into this expression, in both cases, OV is going to be a 1. But I can give you guys some time to kind of work on this. How does 2 minutes sound? Yeah, let's do it for 2 minutes. All right, 2 minutes has passed. We got one confirmation in the text channel, and that was correct. For the top example, for the bottom example, we have basically all the ones become zeros and all the zeros becomes ones. So instead of having the left conjunction being true, we're going to have the right conjunction being true, and OV itself is going to be true because one conjunction being true means the entire disjunction is true. Yep. Because remember, what looks like multiplication is conjunction. So when we look at 0, 0, 0, it is false and false and false. And when we look at 1, 1, 1, it is true and true and true, which is true. So when we have false or true, then the end result is true. So you have to remember, we are not looking at multi-digit binary numbers. Each 0 and each 1 is a Boolean true-false value, and this is a Boolean expression. All right, so does that help? Because this is done to address the early issue of, kind of going through some examples so that we know how to do this. All right, so assuming, oh, okay, here comes some text message, and we can apply this to some of the other examples that we have done too. So I am going to once again copy this equation, and we'll copy it to some of the earlier examples. Yes, that plus is an OR, because the whole thing is a Boolean expression. There we go. So now we are going to work on these few examples on this slide. And there we go. All right. So we have 3 more examples here. We got x, y, and this is d, x, y, d, x, y, d. So let's figure out what overflow should be for each case. Okay, so we'll figure out this one. Overflow is, overflow is, overflow is. Now, there's a quick way to do it. Okay, the quick way to do it is to look for one or the other pattern. If it is not one or the other, then overflow is going to be false. Okay, in other words, you're either looking for 1, 0, 0, 1, 0, 0, or you're looking for 0, 1, 1. Okay, so only those 2 patterns will give us an overflow of 1, meaning that this one doesn't fit that pattern. Overflow is going to be a 0. This one here, we have 1, 1, 0. Once again, it doesn't fit that pattern. Overflow is going to be a 0. And then over here, we have 1, 1, 1. Overflow is also going to be 0. All right. So that is how we come up with the overflow. And the reason, okay, if you remember, the whole reason of trying to get to the overflow is because the sign flag would say the opposite when there's an overflow. Okay, so now we want to combine both of them. Okay, and I'm gonna go all the way to, yeah, I reset my tablet, and it wants to reteach me everything about the tablet now. All right, so now we want to look at both of these and go like, this is the sign, this is the overflow, and this is whether x is less than y signed. All right, so we'll take a look at this table here. Actually, I don't need it to be this big, but it's okay. So when overflow is false, okay, when there's no overflow situation, we can trust the sign flag. Okay, the sign flag being the most significant bit of the difference. So if the sign flag says it's false, then we'll say, yeah, we know that x is less than y is false. When the sign flag is a 1, then we know x is less than y is true. When we do have an overflow situation, then the sign flag would actually say the opposite of what it is supposed to be. So when the overflow is a 1, then if the sign flag at the same time is saying false, then we know x is actually less than y. Okay? And in this case, when overflow is 1, when there's an overflow situation, and the sign flag of the difference is 1, then we know x is not less than y, like that. So now we look at this picture and go like, so we are basically saying the sign flag on its own is not enough to tell us whether x is less than y. The overflow flag itself, by itself, is also insufficient to tell us whether x is less than y. They have to be combined in a certain way so that we can actually end up with the correct conclusion of whether x is less than y if we choose to interpret the values to be if we choose to interpret the bits in a signed fashion. So now we want to look at this and go like, is there a way to, is there a Boolean operator where we can combine the sign and the overflow flag so that we end up with this particular bit pattern here? And Paul is right. There's exclusive OR. So if you use S exclusive OR, plus inside the circle is exclusive OR, overflow, then we end up with exactly the right conclusion of whether the minuend is less than the subtrahend. And that's why we give this particular expression its own name. Well, I do. It's called the L flag. L flag because L is the first letter of less than. So when the L flag is a 1, then we know that x, the minuend, is less than y, which is the subtrahend, if we choose to look at the bit pattern as a signed representation of a value. Are we okay with that concept? I'm gonna give you guys more time to think about that, and if you do have any questions, please go ahead and ask. Curtis is asking me for one thing that I cannot do very well, which is to repeat myself. I'll try, okay? Because I'm not trying to not answer the question. It is just mechanically I cannot remember what I said. The L flag is a 1 if and only if x is less than y if we choose to look at the bit patterns as a signed representation of values. I believe that's close to what I said. All right, so I'm not seeing any further questions. So I will basically go back to the notes. Now the notes has a whole bunch of more stuff here, but it does come to really just the same conclusion that we need an L flag to define, here we go, we have, O being overflow, same definition. I might have, reversed the left-hand side and the right-hand side, but that's kind of insignificant because disjunction is commutative. So, A or B and B or A are really the same. This part here is doing the analysis of what is the actual result of the comparison when we know what the sign flag is and what the overflow flag is. So it's basically the same stuff that we just talked about, just presented in a, I guess, more boring, fashion. And then food for thought is mentioning that now we can see how the subtraction of two signed binary numbers can overflow the result. What about addition? So the idea is, can we extend this line of reasoning to figure out the overflow formula for addition, binary addition? Let's do that. Okay, let's do that. All right, so let's think about, for addition, what would indicate an overflow situation. So we have x, we have y, it is a subtraction, and we have two additional rows here, okay, one being q, one being t, but they are not really that important. And then we have d over here. Now these are the most significant bits, okay? In other words, instead of saying, the most significant bit of x, the most significant bit of y, the most significant of d, I'm just going to call these x, y, and d over here. But this time we want to deal with addition. Remember, this is for subtraction. So when we want to deal with addition, then instead of q and d, we just call them slightly differently. We have k and s. So now the question is, how is overflow defined for addition? In other words, we know it's going to involve x, y, and s. It's going to involve x, y, and s. And it's an or in between. The question is, where do we put the negations? So the question now is, what does not make sense in terms of the sign of an addition? That's all it's asking, okay? So immediately coming to my mind is, if you add two non-negative quantities and you end up with something negative, that doesn't make sense. In other words, when x is a 0, y is a 0, but s is a 1, then it doesn't make sense, okay? So that means we have to negate the zeros, and then sign is not negated because that one needs to be a 1 in order for this combination of sign bit to be not to make sense, okay? Because when something overflows, the sign flag doesn't make sense. So the opposite is when x is negative, meaning x, the most significant bit of x is a 1. Y is also negative, which means the most significant bit of y is also a 1, but somehow the sum is non-negative, which means the most significant bit of the sum is a 0. So in that scenario, x, y do not need to be negated, and s needs to be negated. So this is the equation or the formula to find out whether after an addition, the result of the addition, the sum, is overflowing. But it is not useful for comparison, okay? It's just that, for addition, there's a different way to define the overflow. All right, so I do want to relate this back to CISP360. So in CISP360, we were introduced into the int types, right? So you have, a char is technically an 8-bit signed integer. So now the question is, what if you're adding something and somehow you run out of the range? In other words, the result of a calculation is going to exceed the range of values that a particular integer type can represent. Unfortunately, it's not going to be anything spectacular when it is supposed to be. Because when that happens, if you do the same thing in Visual Basic, it will give you a runtime exception. It will tell you that the result of an addition is exceeding the range of what can be represented using an integer. And it will give you a runtime error whether you like it or not, and then the program will stop and tell you which line is offending. That is good, because now we can at least know that there's a problem. C, C++, and I believe Java is the same way, will silently fail. Meaning that it will just truncate everything. It will do the modulus math, and it will just, go like, okay, since we all understand everything is modulo 2 to the power of 8, 2 to the power of 16, or 2 to the power of 32, or 2 to the power of 64, it's perfectly okay. Because we all understand this is, it's all based on modulo arithmetics. So it's going to fail silently. If you add 1 to the most positive value for a signed integer, it will become the most negative value. Yep. And it's going to do that without giving you an exception, without any warning, without anything. You cannot even detect it if you wanted to. So you would need a conditional statement of your own if you want to catch those situations. So I just want to relate this back to C because it's going to fail silently. So that's bad because your program is not going to crash right there. It's going to crash later, which is a problem. Which is a problem because if it fails later, then you have to trace your way backward, and executing a program backwards, at least in your mind, is not easy. That makes debugging difficult. So that's basically signed comparison. And unsigned comparison, once again, is easy. We just look at the overall borrow flag, and if it is the overall borrow flag is a 1 if and only if the minuend is less than the subtrahend in a subtraction. When we choose to look at the bit patterns as unsigned bit patterns, unsigned representation of values. So that one is easy because it relies on one single flag, the borrow flag, to reflect the ordering of the minuend versus the subtrahend. All right, so that's it. Okay, that's comparison. That's binary number comparison, which is basically based on binary subtraction. So are we good so far? Do we have any questions? Are we relating, the concepts? Do we understand this expression that in parentheses are conjunctions, and then we are doing an or between the conjunctions? So all of this stuff here, I'm just going through a checklist just to make sure that everybody is good to go. All right, thank you. Thank you for the confirmation. So with this module done, I'm just going to move on to the next one. So once again, if you have any questions, do not hesitate to ask me, because otherwise I'm just going to move forward and forward and forward, which may or may not be productive in the long run. All right, so we are moving on to floating point number representation now, which is a very interesting topic. It is not difficult per se. It's just a different way of looking at things, but you still need to remember some basic math about exponents and logs in order to fully understand how floating point numbers work. So what we'll do is we're gonna ease into this particular module by first talking about something that I'm hoping people are familiar with. And that is scientific notation. So I'm going to use the tablet here, okay, open a new page, and we'll talk about base 10 scientific notation. So we'll write it down, base 10 scientific notation. I'll be honest, okay, if someone has no prior exposure to base 10 scientific notation, this entire discussion will suck. It is going to be difficult if people have no prior exposure to scientific notation. No, I'm not talking about individual people. I'm talking about the scenario, okay, being a difficult scenario. So it is not a problem of the individual, but it does relate to whether someone has experience or knowledge of scientific notation. So I'm going to start with this, okay? So we'll start with, let's say, world population. So I'll do a quick search to find out what is the approximate world population at this point. So on the side, I'm just looking for world population, and it says it is 7.674 billion, and that's from 2 years ago. Okay. All right. So we'll go ahead and try to write this number as a scientific notation. So on the side, you cannot see it just yet, but I am writing it on the side. There we go. All right, so this is the scientific notation of the same quantity, because it is what it is saying is this is 7.674 times 10 to the power of 9. So this little e here is really just a separator, so that we can separate from what we know as the mantissa versus the exponent. And because we are using base 10, this is an exponent of 10, which is how much we raise the power of 10 to. Is that okay? Does everybody understand this particular example? Okay, very good. Now we're going to look at the mass of an electron, because we want to go for something that's relatively big and then go for something that's relatively small. So we'll look for that again. Okay, we'll look for mass of electron. As small as it is, it still has a mass, and it is this number here. So this number is not in scientific notation, okay? It is telling you it is 9.1 blah 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 times 10 to the power of negative 31. So we want to turn this into scientific notation, and that's really easy, because all you have to do is to say this is 9.10938.356, and then a lowercase e followed by negative 31, and I'm switching back to the tablet now so you can see it. So this part here is the scientific notation of the mass of a single electron in kilogram. Okay? And some of you are going to say, but Tech, this is awfully bad, because why do we use kilogram when it is such a small quantity? Don't we want to use just grams, right? Well, that's pretty easy, okay? Because 1 kilogram has 1,000 grams. So if you want to adjust the unit to only have to deal with gram, we don't have to do a single thing about the mantissa. We only have to do something about the exponent, okay? Because instead of having 10 to the power of negative 31, when we measure in kilogram, what do you think is going to be the exponent of 10 when we want to measure in grams? Oh, okay. Not the E notation. So we have to, okay, but what are we going to do to the negative 31? Are we going to add 3 to it, or are we subtract 3 from it? And it is exactly, there are 1,000 grams to a kilogram. So when we measure in grams, we have to multiply by 1,000, which is accounted for by increasing negative 31 to negative 28. There we go. All right. Does that make sense? So Paul is right. I haven't checked, but Paul is usually right. So the notation of using times 10 to the power of something, is the quote-unquote scientific notation. But I'm going to use that term loosely in this class, and I'm going to refer to this as what is known as the E notation as the scientific notation. All right, so looks like we're getting a pretty good handle on, basically separating into the mantissa and also an exponent component. Okay, all right. So now the question is, why do we need this type of notation? Well, the question is, how do you represent really large values and really small values when we only have a finite number of bits, binary digits? So let's think about 64 bits, okay? Because a lot of computers use 64 bits as the width of the data bus. So we want to look at what is the range of value we can represent using 64 bits. So if you are only going to use either the signed or the unsigned representation that we talked about using integers, then you are talking about -2 to the power of 63 to +2 to the power of 63, the whole thing minus 1 for signed integer representation. Or if you choose, you can also use the unsigned representation, which is from 0 to 2 to the power of 64 minus 1. So it seems like we're dealing with pretty large values here. Why do we need to go any more? Well, as it turns out, it's not really that large. Okay, so when you look at this value over here, it is about 18 times 10 to the power of, okay, now I have to remember. I cannot remember. Darn it. I know it is 10 to the power of 18, and it is about something. Okay, we can look it up. And Google search is interesting because it can actually do calculations for you. So we can actually enter 2 to the power 64 minus 1. And it is this particular value. So I was close, not entirely right, but I was close. So I'm going to write it down here. 1.8 something times 10 to the power of 19. Okay, switch back to the tablet. All right, so when we look at this value, it's approximate. Okay, there are a lot more digits to it. It's an approximation. But the point is, even though it looks like a really huge value, I mean, certainly this is way more than what it takes to represent my net worth. Okay, I mean, being able to represent negative values can be helpful in that case, but it's a huge value. Even compared to the national debt of the United States, this value is still pretty big. I mean, if you look at this value here, it is still pretty big, when you say, okay, but can it represent the national deficit, of the United States? The answer is, yeah, we can do that. Easy. But when you look at this as, can we represent the mass of a neutron star in kilogram or even in tons? Maybe not. Okay, I'm not really sure. But there are values out there, okay, in physics, in natural science, where this range is not even close to what we need to represent the values that we need to store, that we need to process, that we need to calculate, and so on. So that's one problem. The other problem is using the way that we interpret the bits. Okay, I'm going to give you the sigma notation. So I going from 0 to, let's say, 63 in this case, d of I times 2 to the power of I. Using this method of interpreting the bits will only be able to represent integers. Okay, if you want to represent the quantity of pi, you can't. Okay, because pi is, well, first of all, pi is an irrational number, which means, even if you have to have an infinite number of digits to correctly represent pi. But even if you say, I'm okay with only up to like 3 significant digits, okay, it cannot do it either. Okay, because this is going to give you an integer. So the best it can do is to say pi is 3. Okay, and if you use pi being 3 in calculations, it's going to be way off. Okay, I cannot trust anything built based on pi is 3. That's just not going to work. So we have these problems, okay, and we also have quantities that are way smaller than 1 but greater than 0, okay, such as the mass of a single electron. So integers are great if you want to maintain the index into an array, if you just want to count something. So in general computer science programming, integers they're great. Okay, they can be used in a lot of things. but they cannot do certain things that we want to do in scientific type of computing. So that's why we want to use the scientific notation. But the scientific notation that we have talked about up to this point, or the Yi notation, is in base 10. So now the question is, but inside the computer, everything is base 2. Okay, so how do we convert, how do we store this kind of value and this kind of value in base 2, okay, using only binary digits in bits? Okay, well, the idea is same idea. There's nothing strange about binary scientific notation or base 2 scientific notation. In fact, we have seen something that can be very useful to illustrate that concept. So, switching to a new page. Let's go ahead and think about this base 10 value, or this value in base 10. Okay, so this is a value in base 10, and I'm going to emphasize this is in base 10 by using a suffix of 10 over here. And now I'm going to look at this and go like, let's convert it into a base 2 number. Okay, I'll give you guys maybe 30 seconds to do it. I'm actually looking at the time. I am giving you 30 seconds to do this. All right, 30 seconds is up, and let's go ahead and find the answer. So this is 16 plus 2 plus 0.5 plus 0.125. All of these are powers of 2. And 16 is 1 followed by 4 zeros. And 2 is 1 followed by 1 0. 0.5 in base 10 is 0.1 in base 2. And then 0.125 in base 10 is okay, let me think, 001 in base 2. And if you are looking at this and go like, I do not understand about why the 0.5 is 0.1 in base 2, you really need to go back to base conversion, because when we talked about base conversion, we talked about this part already. Because the position of the digit to the right hand side of the point tells us how negative it is using the base of that particular number. So in this case, 0.1 in base 2 is 1 times 2 to the power of negative 1. And then this 0.001 in base 2 is 2 to the power of negative 3. And there's one of those. So when we add up all of these things, we have 10010.101 in base 2. So this, I believe, is something that we have talked about already sometime last week when we talked about base conversion. And if this is sounding familiar but you are getting a little rusty, you might want to review that material. Okay? So we look at this and go like, yes, even for people who remember the base conversion, they look at this and go like, but I don't see any scientific notation here. There's no exponent of base 2. But that's okay. I can fix that. Okay? Because I can simply say this is the same quantity times 2 to the power of, guess what? 0. And then you guys are going to go like, but that's cheating, Tack. Everything to the power of 0 is 1, and you can always multiply something like that without changing the value of the expression. You would be correct, okay? But I'm not done yet. Oops. I just shifted the point to the left-hand side by 1. So now the question is, how am I going to adjust the exponent of 2 so that the equality is maintained. What do you think? So let me present this in a slightly different way. This one here used to tell us how many 16s we have. Now it is telling us how many 8s we have. This one over here was telling us how many 2s we have, and it is now telling us how many 1s we have. In other words, if you just focus on this part here, the value is halved. But if I want to maintain this equality, what do I need to do about the exponent of this 2 over here so that we can make up for the Mantissa being halved? Well, not the Mantissa, but the other part of the equation being, the expression being halved. Eric has the right idea. Not really. Yep. We put a 1 here. Okay, because if one side of the expression is halved, I need to double the other side in order to make up for that difference. Alright? So it is not 2 to the power of n plus 1, it is just 2 to the power of 1. Because we move the binary point. It is not the decimal point anymore, it's the binary point. I move the binary point to the left by 1 position. Alright? And I'm not done yet. I can move it again. Okay, I know some of you are going like, this is really going to be boring. Okay, and I can do this again. And one more time. And my watch is reminding me to take roll. So we'll take a short break from this math here. And then we'll go take roll. We'll do some activity here. Alrighty. Unfortunately, every time I add an activity, it always adds it to the end of a particular canvas module. So now I have to move it all the way back to where it is supposed to be, which is right around the topic that we are on at this point. Oh, okay, I went a little bit too far. There we go. So I'm going to move it here. You can't see it yet because I have not released yet. So I'm going to specify the question first. So the word is going to be exponent. And the word is exponent, E-X-P-O-N-E-N-T, all lowercase. And right now is, I'll call it 23 right now. I'll give you guys up to 28. June 16th, 6:28 p.m. Save and publish. There we go. All right. And I'm going to type that word in the text channel. Exponent is the word for row taking. So now you just have to copy and paste. I will answer that question in just a little bit. All right, so I am going to guess that most people are done with the exponent. Okay, so I will go fix that for you. Next time, just copy and paste. And tomorrow is Thursday. You are correct, Barak. So we do have class tomorrow. That is what you have signed up for. A summer class that has 4 units. Yep, even as a full semester class, it is fairly compressed, it's fairly packed. So as a summer class, it is, guess what? Twice as packed. It's kind of like those, candy commercial, where they say, if you think this is intense, wait until you try our new version of the same candy because it is twice as intense. Yeah, Starburst or something like that. I didn't say that. I did not quite say that. I just said that you guys signed up for this, and it is on the schedule that we are meeting from Monday to Thursday, from 5:30 to basically 8:20. But it is written in the schedule when you signed up for this class. So that was my point. My point was, it was on the schedule. I did not change anything from the schedule. So I'm only teaching the class as advertised. Okay. All right, so back to the tablet. Back to this scientific notation business. This is actually scientific notation because I have now expressed the whole thing with a mantissa and times, this is the base and this is our exponent. So the answer, so now I'm hoping that we have made it clear that yes, you can actually use scientific notation in other bases. Okay, it's not just something you can do in base 10. You can do the same thing in base 2. And for our drunk octopi, they can also do it in base 7. Although that would be it's just a very strange base to use because it is a prime number, but there's also no reason why we cannot do that. But in a computer, oh, I shouldn't say that because that's just stupid of me, because 2 is a prime number, and yet we use base 2 all the time. So using a prime number as a number base is nothing awkward at all because 2 is a prime number. All right. So getting back to this, okay, we now have a mantissa and we have a base. So the question is, what qualifies as a mantissa? Okay, so mantissa, if you look it up, has a very specific meaning. But if you think about what a mantissa is if I use m, to represent the mantissa because I don't feel like typing or writing the entire word out, it is usually greater than or equal to 1, but it has to be less than whatever base that we are using. So in base 10, the mantissa should be less than 10. in base 2, the mantissa should be less than 2, but it also has to be greater than or equal to 1 in order to be called a mantissa. Okay, so that's kind of what the mantissa is supposed to be. And then, and then we can adjust the exponent in order to specify whatever value we want to specify. So even though the mantissa has a very short range of value that it can represent, by adjusting the exponent, we can scale that mantissa to represent values of a huge range. So that is the whole idea of base 2 scientific notation. So are we good with this concept? Are we good with this specific example of how we converted 18.625 in base 10 into a binary scientific notation? All right. So looks like we are good here. Oh, okay. Several people are typing.
Also, sir.
Yeah.
When it comes to the base multiplication, it goes both ways too, right?
What do you
Like
mean by
if we
both
expanded
ways?
it, if we expanded it to the left by another binary digit and then multiplied it by a base of -1, we would get the same thing as, well, 16.6 or 18.625, right?
That is correct. It can go the other way too. So I'm going to give you an example. That's a very good point. Okay, so in the text channel, there's a question. Will the base 2 number always have the same number of digits after the decimal point? I guess the decimal means the point as the base 10. The answer is no. It doesn't have to be the same or even close, because there are certain values in base 10 that we can use a finite number of digits to represent that is impossible to represent using a finite number of digits in base 2. Like 0.3, okay? 0.3 in base 10, cannot be represented using a finite number of digits in base 2. It's just like 1/3 in base 10. I mean, 1/3 as a value. If you want to convert into a decimal number in base 10, it's going to be 0.33333 and so on. So it's the same concept. Okay, next page. So let's deal with something that's on the smaller side. Okay. I'm not even going to bother to write this as a decimal number because we'll just end up with a whole bunch of zeros, which is totally confusing and not necessary. So I'm just going to specify the value that I want to represent as 13 divided by 1024. So we look at this and go like, how shall we do this, right? Well, the first thing is to separate the 13 from 1 divided by 1024. So now we have 13 has 1 8, sorry, 1 8, 1 4, no 2, and 1 1. So it's 1 0, 1 1 0 1 in base 2. And the other side is 2 to the power of -10, because 1024 turns out to be 2 to the power of 10. So because 1024 is the denominator, it's 1 divided by 1024, so we represent it as 2 to the power of -10. So now we look at this and go like, do we have a scientific notation? The answer is no. Almost there, but no, because 1101 in base 2 is not less than 2. So we somehow have to shift the point around so that it meets that requirement. And then somebody's going to ask, but where's the point to shift? There's always a point here, okay? There's always a point. It's just that in most cases, we don't have to write that point because there's nothing to the right-hand side of that point, so we don't need the presence of that point. But that point is kind of always there. So now we just have to say, okay, we need to move this point 3 digits to the left. Okay, so it becomes 1.101 in base 2 times 2 to the power of what? Every time we move the point to the left, we have to add 1 to the exponent of 2. So we have -7 now. That is correct. Good job. And if someone is saying, but Tack, this is it's still partially in base 10 because this -7 is in base 10. Well, that's actually okay. Okay, because it is just a quantity. Okay. Now, if you really want to turn this into scientific notation, using only base 2, okay, we can do that. There we go. Now we have everything in base 2. It's just a little bit harder to read, but it's the same thing. I mean, 2 is 10 in base 2, and then 7 is 111 in base 2. So we can do it that way too. Okay. So I think, we are now ready to look at the IEEE double precision floating point number format. Okay. Yeah, that's a mouthful. From here on, I'm just going to say double. Okay, instead of using the entire phrase, I'm just going to say double. Should have used that for row-taking purposes because I think that's actually a more representative term of what we are dealing with here. Alright, so we'll go ahead. I think I opened this up already somewhere. Can't find it. Okay, so let me show you a tool that I have. I'm not sure whether you guys can see it. Probably not. It's a little extension on the browser that allows me to search the title bar of a page because I constantly lose things because I have too many tabs open. But it does let me kind of get back to a particular page or tab really quickly. Alright, so this is floating point number representation, and we are going to go here, and I just thought if somebody already had a good picture and explanation of the double precision floating point number, why do I want to repeat that, right? So we just go to Wikipedia and go straight to a picture. There we go. So this picture is telling us how we utilize 64 bits. Bit 63 is the sign of the entire value. Okay, so this sign applies to the entire value. If the sign bit or bit 63 is a 1, then we are dealing with a negative quantity. If the sign bit or bit 63 is a 0, then we're dealing with a non-negative quantity. So this sign is, so we are not using 2's complement or anything like that in the context of a floating point number. Now we have the exponent. Now this is actually a misnomer. It really should be called a biased exponent. I'll explain that later. It takes up 11 bits. So now we have 52 bits left. It is simply named fraction. It is the fractional part of the mantissa. In other words, this is whatever is to the right hand side of the point. So there's implicitly a 1 point and then followed by these 52 bits over here. Okay, so how are we going to use this to represent the values that we have played with? Okay, so we're going to reuse our examples to illustrate this point. So let me switch back to the tablet, which is right here. Let's work with this one first. Okay, so when we look at this value, 13 divided by 1024, it is non-negative. So we know, so let's use, I'm just thinking about the notation. The sign bit, okay, the sign bit is going to be a 0 because the value that we are representing is not negative. Alright, so now we look at the exponent. Okay, this is our exponent. Oh, actually, back. That is not our exponent. This entire thing is our exponent. Okay, so this is where it looks a little bit weird because it is a biased exponent. So I'm going to use E2 to represent the exponent of 2. We really want this to be -7, but the actual exponent that we store into the 64-bit double is biased. So the bias amount is 1023. Don't ask me why it is not 1024. It is 1023. Okay, IEEE has decided it is 1023. Okay, so we are not going to discuss this. We are not going to argue. We'll just say the biased amount is 1023. So the actual exponent being represented is biased by 1023. And that turns out to be what? 1016, I think. There we go. So E is actually 1016, okay? Or whatever integer we want to put into, let me switch back to here, into this green area here is going to be an unsigned integer 11 bits wide to represent 1016 in base 10. So we'll deal with that later. What about the fractional part of the Mantissa? This is our entire Mantissa. So the fractional part of the Mantissa is only this part. This is the fractional part of the Mantissa. So we'll say the fraction part is going to be 101. And someone's going to say, but Tech, we are expected to have 52 digits over here. We only have 3 at this point. Well, that's easy. We just go like ... 0. So we basically say there are 52 binary digits here. I just decide not to handwrite the other zeros. Okay. So now we have all the essential components. Okay. Bit 63 is a 0 because this is the sign bit. And then the next 11 bits would be the unsigned representation of 1016. So now we have to convert 1016 into a binary number. It's not going to be super duper easy because 1016 has a whole bunch of ones in it. So instead of figuring out where the ones are, we're going to go figure out where the zeros are. Because what we know is 1023 is 10 ones, okay, in base 2. So 1023 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is how 1023 looks like in base 2. So now we look at the difference between 1023 and 16, and we figure out that we need to remove 7 from it. So to remove 7 means these 3 need to be turned into zeros, and now we have 1023 in base. Now we have 1016 in base 2. But there are only 10 digits over here. We'll have to pad a 0 to the left hand side, so now we have 11 digits. So now we have bit 62 down to bit 52. Oh, okay, we need more space for that. So I'm gonna spell out 0, and then we have 5 ones, 1, 2, 3, 4, 5, and then 2 more ones, and then 3 zeros. All right, so this is from bit 62 down to bit 52. Now we need to work with bit 51 all the way down to bit 0. And that would be just the fractional part of the Mantissa. So the 1 point, this one of the 1 point, is never actually stored in a double. It is always just implied. Okay, it is only the fractional part of the Mantissa that is actually represented in bit 51 down to bit 0. Okay, so that would be 1, 0, 1. And then a whole bunch of zeros down to the least significant bit. I'm looking at the time. Okay, that's good. So we are good in terms of time. So now we have this bit pattern, which is 64-bit wide. And how do we check whether Tech is doing this right or not? Because I can claim all I want and say, yeah, if you look at this 64-bit representation using the IEEE double precision floating point number format, it should be representing 13 divided by 1024. I can claim that, right? But none of you is going to believe that. Well, you should not, because I am known to make a lot of mistakes. Not that I want to mislead anyone, but sometimes I do make mistakes. So now the question is, how do you make sure that I did not mess up in this conversion process, right? So I'm going to show you a technique to do this. And we're gonna use a technique where you don't need to install anything, so that you can do this on your own if you want to. And the resource is onlinegdb.com. And earlier somebody asked, can a Raspberry Pi can it be used to do all the homework assignment for this class? The only thing I'm not 100% sure is, can you get Java running on a Raspberry Pi? If you can, it should be doable. But I think getting a Raspberry Pi to work, well, okay, if you already have one, then it's easy. But if you don't have a Raspberry Pi, it's probably easier to install Windows subsystem for Linux, because that way you can just use your Windows machine and run Linux on the side with very minimal overhead. So that's just just a recommendation. Alright, so the first thing I'm going to do is to pound include stdint.h, okay, because this is the standard library for integers. It defines a whole bunch of types, a bunch of type defs. And I'm going to change the program, and we'll use uint 64_t, which explicitly is specifying a type that is an unsigned 64-bit integer. Because if you don't use these destination and you just go like, oh, we can use a long unsigned, or unsigned long, or unsigned long long, those are really fuzzy, okay? Because there's no actual agreement on which one will specify a 64-bit integer. This one we know for sure. We'll just call that x, and the program is going to say x equals to 0, and that's it. This is my entire program. And you go like, I really don't see how this program can be used to check whether Tech was right in his conversion. So we're gonna give it a try. First thing first, we have to select the language. It is just regular C, not even C++, okay? If you want to use C++, that's fine, because C++ is, for the most part, not entirely, but for the most part, it is a superset of regular C. And we're going to use the debugger. Just click on debug, and now we have the debugger prompt. And I'm going to put a breakpoint here on line 18, just so that I can pause the program's execution at some point. And I'm going to bring the debugger window up a little bit. So I'm going to run the program, R for run, and now it is at a breakpoint. Now at a breakpoint, I can print the value of x, which is also displayed on this side. Nothing surprising whatsoever, right? Okay, so I need to make sure that my browser does not automatically discard this page, because I have an auto tab discard, which basically means if a tab is idling for a while, it is going to automatically close the tab. Not close the tab, but to suspend the tab, so that it releases the memory used by that tab. So I have to turn it off, because otherwise when I come back here, it's going to be gone, which is not going to be good for our demonstration here. Alright, so we get to this and go like, this is a whole bunch of zeros and ones, and there is no way you can actually specify a value in base 2 in C. It just doesn't exist. So we have to convert it into base 16 first. So to convert from base 2 base 6 to base 2 to base 16, you group these things by 4, starting on the left hand side. So we have that as a group of 4. This is a group of 4. This is a group of 4. And I am looking at this and go like, did I miscount something? No, I did not miscount something, but I did write an extra 0 when it's not supposed to be there. Oh, okay. Never mind. When I copy the value, I copy incorrectly. So let me just double check. 0, and then we have 1, 2, 3, 4, 5, 6, 7 ones. 1, 2, 3, 4, 5, 6, 7 ones, and then 3 zeros. That looks right. Okay, so I did write an extra 0 there. So 1, 0, 1, 0, and then the rest are all zeros. So that's an easy part. Okay. Once you have grouped the bits in chunks of 4, then each chunk, each group of 4 bits would correspond to 1 digit in base 16, which is hexadecimal. So this is 3, this is F, this is 8, this one is A, and then the rest are zeros. Okay, and because one hexadecimal digit is corresponding to 4 bits, so we know the non-zeros, 1, 2, 3, 4. Okay, the 4 non-zero hexadecimal digits are accounting for 16 bits already. So that means the rest, okay, there are 16 bits over here. So the zeros, the zeros on the right hand side, they have to account for 48 bits. So that means we need to have 12 hexadecimal zeros. Okay, so let's go ahead and enter this number. Okay, I'm going to switch back to GDB, and we say set var x equals 2, and in C you can specify hexadecimal. If you use the prefix of 0x, then you can go ahead and use base 16. I will explain base 16 in the next class, but for now I'm just gonna punch it in. So 3F8A followed by 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Press the enter key. Everything looks good. And when you look at x here, you go like, tag, I think you lied, because this value here is nowhere close to 13 divided by 1024. Well, that's because x is an actual unsigned 64-bit integer. This is the interpretation of these bits, assuming that we want to look at that as an unsigned 64-bit integer. You can't see the x variable value. It's right here. Or here. This is in hexadecimal, that one is in decimal.
We can't see it because of your
Oh,
camera.
because of my face, because of my big fat face. Okay. Yes, I said that. But you can also see it here. That's also the value of x in hexadecimal. Okay, we can also print x, same thing. There we go. But we can agree that this is not 13 divided by 1024. So how do we make GDB to interpret those bits as if they are bits of a 64-bit double precision floating point number? That becomes the question. So some people would say, maybe we can just cast it, right? Casting doesn't work in this case. And why? It is because casting is already assuming x is an unsigned 64-bit integer. So the casting is simply saying, okay, so we are dealing with a huge number starting with a 4, and we want to represent that huge value as a double, which is not what we want to do. I'm running out of time, so I'm just going to give you the answer here. So we're going to do a dereference of something, and that something is casting the address as a double. So we are basically casting the address of x into the address of a double, and then we dereference it. So this time it does work. It gives us this answer of 0.1269 something. That doesn't sound right to me. Maybe right. No, it actually sounds plausible to me. So let's go ahead and print the actual value of 13 divided by 1024. And oh, that's integer division, so that's not gonna work. So we have to cast 13 to a double first, so this way we are forcing the interpreter to also treat the division and 1024 as a double. So now we get that, and you can see how 13 divided by 1024 is exactly the same as the value when we choose to interpret the 64 bits as a double precision floating point number. So this is the verification of this process actually working. So we'll get back to this tomorrow, okay? But it doesn't hurt if you try to review this material. Tonight's lab is very straightforward because I talked about that yesterday already. Tonight's lab is really just part 2 of the 3x3 carry look ahead adder. So for people who might have questions about their own version, whether it's right or not, you might want to watch the YouTube video of my solution, and you can borrow that solution. I'm not going to give you the file. You're going to have to make it yourself, but you can borrow the idea from that video in order to get started on part 2 of that kind of long-ish lab. Are there any questions?
For the people who are caught up, are you going to open up the next lab, or is this
No, because if I keep doing that, then one part of the class is always going to be a little bit ahead of the class, the rest of the class, which makes things a little bit kind of difficult. So if you are already done with part 2 of the lab, you basically have tonight off. I would use that to review the material, but that's just me. But no, there's no new lab other than part 2. Yeah, woohoo. Okay, I just got one more thing to remind people. Okay, so even if you have it done already, I did include the test driver. So you might want to run the test driver just to make sure that you got everything right. So if you were to go to the file submission homework assignment for part 2, there is the test driver circuit and also the log of the correct circuit. So you might want to double check and make sure that is right. The only thing that people might have gotten wrong would be the positioning of the pins, the input pins and the output pins. Let me go back to that description so that you guys can double check your own just to be sure. Okay. Preview would work in this case. All right. So the most important part is in the main circuit of the carry look ahead adder, the vertical and horizontal relative positions of x, y, k0, the sum, and also k3, they need to be exactly like this. In other words, all the input pins should be on the left-hand side, all the output pins should be on the right-hand side. X should be on top of y, y should be on top of k0, sum should be on top of k3, and you can also check the circuit appearance and to just make sure that that is the case, that you have the pins at the right positions, because otherwise your circuit is not gonna be quote unquote pluggable into the test driver circuit, and then the output of the test driver is going to be all wrong. So you got to make sure that this is you just need to double check this for people who are already done with the project. This is just one last thing to kind of double check. Yeah. Otherwise, there's nothing new for part 2 of that lab.
I ask a question here?
Go ahead.
About that, I'm not sure. I feel like there's been a little bit of inconsistency about the case in the labels, uppercase versus lowercase.
Yeah, it's
But
not. It
as long as we're consistent within our own circuit, we should be fine, right?
That is correct. Yeah, the
Okay, thanks.
labels are or the naming of the tunnel. I think it is case sensitive, so you have to be consistent within your own circuit. Other than that, my test driver doesn't care about the labels. So there's no dependency on the labels. There's only dependency on the relative position of the pins in the appearance. All right. Yeah, go ahead.
Also, sir.
Go ahead.
Thank you. So for testing our circuits, as long as we get back that both the test file or the test log that you put out is the same as the same output as our circuit using the test driver, we shouldn't really have to worry about anything in terms of our project possibly getting docked on points. It should be fine.
You still have to be following the instructions, from this lab, today, and also the lab from like 2 days ago. So you have to be implementing K1, K2, K3 correctly, and you have to be using the carry look ahead mechanism in order to get full credit. Is that making any sense? In other words, I do take a look at the actual circuit to see whether it is correct or not.
All right. Thank you.
Yeah. The reason why I said that, okay, I can tell you why I need to check that too. The reason why I said that is because if I only look at the log output, someone can use the built-in adder component inside Logisim and just kind of package it a little bit so that the pins are at the right places, and then turn it in as the project. And then my test driver would not know any better. It would just go like, yep, according to these inputs, it's giving me those outputs and everything is good. But in reality, that circuit is not really reflecting the person who turning the file knowing how to implement a carry look ahead adder circuit. So that's why I still need to open up the circuit file, look into it, make sure K1, K2, K3 are correct, and they are structurally correct, and no one is turning in a carry ripple adder instead of a carry look ahead adder. Because that's the other thing, right? Because when I made the carry ripple adder, I specifically said, no, this is not going to be something that you want to turn in because it is a slow mechanism and we don't want to use it. So I just want to be careful with what I say when I say, I would use the test driver as one criterion to test the submissions, but I will also go into the circuit file just to make sure that someone does not shortcut the whole thing and just use Logisim's own adder and get it done in 2 minutes. That's all.
I'd like to weigh in for just a second. If you go back down to the circuit, when you look at the edit circuit appearance, if you drop the pins out of order by accident,
you can change them.
Right. So you have to move the little blue symbols around to match what you want it to do.
Yes.
And I learned that the hard way, so I don't want anybody else to learn it that way.
Oh, okay. I see.
Yes.
Yeah.
So my P was in my Q position.
Oh.
And then I think the K and the S were also switched.
Oh, that would be, that would definitely be problematic for the test driver, because the test driver is just doing a positional match of the pins and it doesn't really know which one is really which one.
Right.
Okay.
So I thought I'd share that with the class.
Okay.
So nobody else spends an hour on it trying to figure it out.
I have same problem.
Yeah, well, that's why even in part 1, there were a few sentences that emphasized, you do not want to change the relative position of the pins. That's why I put those in. Alrighty. But thank you for sharing. Thank you for letting the rest of the class know about the importance of this. It can be fixed. It's just that you have to be aware of that. And being able to run the test driver, because I'm giving you the test driver itself and also what the log is supposed to look like. So utilizing that as an extra resource to make sure that your submission is going to work on my side is going to be helpful. If you have the time to do it, you'll go ahead and double check and make sure. All right. Any other questions? Any other comments? All right. I'm not seeing anything. So